Hey there, wanted to let you know this is an audio only podcast, and if you get your podcast on Spotify, you can go follow me there. All right, cheers. Welcome back, ladies and gentlemen, to the FRBs podcast. I'm your host, Aphelion, as always. If you're new here, this is a space science or astronomy podcast where we talk about new things going on in the field every week with three stories. The three stories we have for this week, the first one is about James Webb and how it's discovered that the universe is exploding with supernovae. The second article we'll be talking about is an unusual radio signal from an unusual source that is very, very slow. And then we'll talk about fast radio bursts on the other hand. So, without further ado, let's jump into this first story, which is about James Webb and its discovery of supernovae. So, James Webb, or JWST for short, has been on a roll recently with its discoveries, and one of them pertains to a very small region in the sky that is blasting with supernovae. And when I say this region is small, I mean like the analogy for it is a rice grain, the size of a rice grain, if you put it at arm's length. And to me, what pops out is just the fact that it's more of a testament to the size and depth of the universe, because this region is obviously, compared to us, quite big, but because it lays in, far out into the universe, it's almost insignificant, except for the fact that James Webb has found 80 new supernovae in it. And if your mind hasn't not already been blown, that is another stunning fact for you. And if you're still not impressed, perhaps you can imagine trying to mark a rice grain with 80 dots, and seems quite impossible, doesn't it? Hopefully that's enough, because, I'd assume that that's a reasonable comparison to what we're looking at here. But if you're not impressed by that, I don't think you're in the right place, because that's what we do on this podcast. So, yeah. Anyways, the sample also includes the earliest and furthest supernova ever seen. It's one that exploded when the universe was just 1.8 billion years old, and obviously we know that the universe is 13.8 billion years old, so just a fraction of that age is when this supernova occurred, so quite early. And this discovery is 10 times greater than any other discovery of early supernovae. So that 80 number is huge. And before James Webb discovered this 1.8, or a supernovae from 1.8 billion years after the Big Bang, the next best, or the next earliest discovery was 3.3 billion years after the Big Bang. So these are quite some records to break here, and it really sort of encapsulates how great James Webb Space Telescope is. Dropping all the stunning photos was enough, but this is like almost overkill. And yeah, so that's what James Webb has discovered here, and a clear-cut reason as to why it's able to do this over any other space telescopes is because of its infrared light detection and its speciality in that part of the electromagnetic spectrum. A lot of the supernovae from this era in the universe had their light stretched to the point that visible wavelengths became infrared wavelength, and it's because they're so far out, the universe is expanding, that their light is getting stretched. So the term for that is cosmological redshift, and so what it did was it shifted the light from optical wavelengths for the supernovae to infrared. So James Webb Space Telescope was able to pick it up, and it not only applies to supernovae, it applies to pretty much all of the early universe and what you can detect there. So yeah, again, James Webb is just amazing. The specific method that was utilized by scientists with the data to decipher the supernovae was by comparing observations from the region of the sky to determine any changes in apparent brightness. So that would tell these astronomers that there's some kind of transient phenomena that's going on in this region of the sky. And transient phenomena is like sort of a fancy word to say like a temporary event in the universe, not necessarily like, a permanent thing that exists in the sky, but something that, you can observe for a significant duration. Discovering supernovae from corners of the universe like this is particularly helpful because type 1a supernovae are known as standard candles. And I've explained it a couple times before on this podcast, but standard candles are stars or celestial objects whose known luminosity is very predictable or, well known. And so that makes it so that you can just use the difference between the apparent and intrinsic brightness to calculate its distance. The equation that relates these two ideas is known as the period luminosity relation, which was discovered by Henrietta Leavitt, who I did make an episode on. So if you want to check out that episode after, you're welcome to. But that is the logic behind why we classify type 1a supernovae as standard candles and why they're helpful. So, yeah, the fact that these supernovae are from the early universe means these are slightly different from supernovae you might find in, our galaxy, outside our galaxy, or, distant galaxies. These are really, really far out there. And what we're doing here, possibly, is putting cosmic distance markers at the edges of the universe. Supernovae are also helpful when we look at their chemical compositions, which tells us not only about the object's evolution, but the evolutions of stars that are similar to it and around it. The only issues with, completely manifesting this idea that we've found cosmic distance markers for the early universe is that at the end of the day, they are subject to the universe's expansion, which, astronomy as a field is not very clear on. We haven't found like a universal constant for the expansion of the universe. And if we can solve that problem, then maybe it's not a huge issue with using these type 1a supernovae as standard candles, but because all of that is uncertain, it's not like the best way to do distance calculations. So yeah, that is the first story. Our second story here, we're going to transition into radio waves and the study of radio waves with this new research that's being done into an unusual and peculiar object and the radio signal that it is emitting. So astronomers have detected radio bursts coming from the slowest spinning neutron star ever seen. Its rotation is slow enough to the point that it releases a radio signal every hour. Now, to the average person, that's probably nothing special. Like a signal every hour does seem fast, but we have to consider that a neutron star is not a particularly common object. They're really dense, and as they contract, they achieve angular momentum that creates very high tangential speeds. It's like close to a quarter of the speed of light in some really, really extreme cases. And on top of that, the magnetic fields of these objects are unmatched. They are very, very strong. So radio bursts coming only every hour for these things is actually unusual. We're used to hearing more about like millisecond pulsars that have these like extremely small rotation periods, and then we'll talk about fast radio bursts, which isn't necessarily from objects like neutron stars, but I guess it's technically in the conversation. Furthermore, some properties about these radio signals, they're made up of circularly polarized radio waves, which means that the direction of the waves corkscrews around us as the signal travels through space. And this neutron star and its emissions is not only surprising, but is actually theory breaking because as neutron stars age, their rotation slows, and so they can't pump out as much radio emissions. That makes this neutron star here seem old, but it's not really because it's still technically pumping out radio signals. So yeah, it's a little bit weird in that sense. What is intriguing is how this object displays three distinct emission states, as is mentioned by the team leader on this story here. And so the emission states referred to here, they're specifically linearly polarized light, circularly polarized light, and the quiet state for the neutron star. And linearly polarized pulses were the strongest signals, and the quiet state pulses did not appear at all. So very unusual stuff going on here, to put it, briefly. If the signals didn't arise from the same point in the sky, we would not have believed it to be the same object producing these different signals, is another thing that the team leader on this research did mention as well. So the most conclusive theory we have about this neutron star and some of the other similar objects we've discovered, it goes as follows, and this is a quote from some of the studies that were done on this object. The name for the object is ASKAP, and then a bunch of letters and numbers. So anyways, this neutron star is probably part of an older population of magnetars with long spin periods and low X-ray luminosities, but magnetized enough to be able to produce coherent radio emission. So this is the most clear-cut hypothesis, but there are some really, really dank theories about this object, like it might not even be a neutron star. It could just be a white dwarf with a really, really strong magnetic field, because, we don't really know if it's a neutron star in the first place. Which, at that point, it becomes a little bit difficult to justify the theory, because we don't usually see magnetization with white dwarfs. They do rotate sometimes, but the magnetic field is you're going to have to really dig for that one. But a different and slightly more plausible theory is that the object is a part of a binary system where a neutron star or white dwarf orbits another unseen star. But even then, for me personally, I struggle to understand how both objects don't create their own emissions that aren't seen distinctly. Perhaps that could be the point, because we have different emission states. But it's just something to ponder. I think that one's a little bit more plausible than, just it's a white dwarf. But I'd say the clearest conclusion to take out of it is definitely the first one, where it's an older population of magnetars, it's aged, but it's just magnetized enough to the point where the emissions don't make it seem that old. So that is our second story. And our last story here is about fast radio bursts, as I've prefaced one or two times already. If you don't know what fast radio bursts are, the article gives a pretty nice explanation. Fast radio bursts are intense, short-lived blasts of radio waves hailing from beyond the Milky Way that can emit the same amount of energy in just thousandths of a second than the sun takes 3 days to emit. So these are high-energy waves that are reaching us, and they're very, very quick. These are the definition sort of fits for non-repeating FRBs, which is the short form for fast radio bursts. Because there are actually repeating ones which are a little bit more extreme. They originate from objects with stronger magnetic fields. Now, the most curious part about FRBs is their origin, and this part is where the uncertainty comes in. We have a lot of candidates that might fit for where these FRBs come from, but we haven't gotten anything conclusive yet. I think the most support is definitely for magnetars and pulsars, but it could be colliding black holes or neutron stars, or it could be like supernovae. We don't know for certain yet which of these objects might produce FRBs. The most wacky theory I read about was one in 2015 that suggested that FRBs are caused by explosive decays of axion mini-clusters, which gets into probably some very complicated quantum mechanics. But anyways, a recent study on FRBs has now brought light to more of its properties, which might help us uncover the mystery. So first of all, we expected the light to be polarized because the sample of FRBs in this study contained this property. The study looked to investigate the orientation of the polarization of light to understand what happened to the light as it was emitted and as it traveled through space. So kind of going back to this circularly polarized light and linearly polarized light, and sort of, what angle as well, probably. One of the quotes from the articles that describe the research here stated, by modeling how polarization twists and evolves, astronomers could reverse engineer key properties of the FRB locales, their densities and magnetic field strengths. And what the researchers found was not much, but they did find that pulsars were probably out of the picture because the patterns of light from pulsars didn't really match up, and that non-repeating FRBs are not as similar as originally thought. So yeah, kind of interesting that the sort of, I guess, status quo has been that we assume magnetars and pulsars are really strong candidates, but it seems like with this research, maybe not so much, and there might not be as much similarity. So it's still kind of up in the air after the research or after the fact. The research didn't do much to bring like conclusive, like, here are some really good candidates to look at, but it got rid of one of the big ones. And if you further the understanding of the polarization of light in these cases, maybe we'll be able to get rid of more candidates. So yeah, hopefully you didn't find that news disappointing, but it is research that's going on, trying to bring more clarity to the issue. Not very often do we see people research non-repeating FRBs. It's typically repeating FRBs that get a lot of the attention, and this is sort of a start of probably something new. So yeah, that is the last story of this episode, and thank you very much for listening all the way through. If you enjoyed what you have been listening to so far, I would sincerely appreciate a subscribe on YouTube and a follow on Spotify if you're listening on Spotify. And yeah, until next week, I will see you all later. Peace.